Hello everyone, and welcome to the post lab of part 1 of the Newton's second law lab. In this part, we were looking for a relationship between the acceleration and the force with constant mass. So eventually, you had to make a graph of acceleration in meters per second squared and force in newtons. And when you made that graph, it looked like that. It was a linear graph that went through 0, 0. And as we've seen many times this year, when you have two variables and they result in a linear graph that goes through 0, 0, that means the relationship between those two variables is proportional. So we can say that the acceleration is proportional to the force. Probably not that shocking, right? If you double the force, if you push twice as hard, it accelerates twice as quickly. Now remember, acceleration is not velocity. Acceleration is how quickly you change your velocity, right? How quickly it's speeding up or slowing down if we're in one dimension. Okay? If we triple the force, you get 3 times the acceleration. If you cut the force in half, you get half the acceleration. In this part of the lab, though, that's only true if you keep the mass constant, which we did in this part of the lab. So now what we can do is we can build a math model, right? Y equals mx plus b, because it's a linear graph, of course. The y variable is what we graph on the vertical axis, which is the acceleration. That's going to equal your slope. You can, of course, just put yours in, right? But I want to show you all the slopes gathered throughout the day. Right? And these are the slopes of everyone's acceleration force graphs. And if you look, they're all pretty close to one another. You see a lot of 1.2 somethings, high 1.2s, some 1.3s. Right? Overall, the average as a class is 1.29, which to 2 sig figs is quite obviously a 1.3. If you look, sure, there's a little bit of error, 1.34. Right? Let's see here, 1.2, ooh, there's a lower one, a 1.228. Right? But still, that's not really that far off from 1.3. So should be pretty confident, right, that the class average is in your slope's ballpark. And we will talk a little bit about where some of that error may have come from in a couple of minutes. So in order to interpret what this slope means, we of course need units. We find units on a slope the same way you find a slope, rise over run. So in this case, the units of rise are acceleration units, meters per second squared, and the units of run are force units, or newtons. So we have a slope of about 1.3 meters per second squared per newton. And of course, one of the things we want to know is, what does that tell us about the acceleration and the force? Well, remember that, of course, a slope is a rate of change. It tells you how quickly one variable changes when you change the other. So if we do a little for every statement, it would be for every additional 1 newton of force, we get an additional 1.3 meters per second squared of acceleration. When you change the force this much, you change the acceleration that much, right? Hopefully you're getting a little better at writing these for every statements for linear slopes of linear graphs, linear relationships, proportional relationships. However, we can do something else kind of interesting with these units, which is that we can simplify them. Right? Based on what we know about a newton and what we found out about a newton in the last activity, the definition of a newton activity. So let's check out these units. We've got units of meters per second squared per newton. But do you remember what we decided a newton actually stood for? 1 newton was the force required to make a 1 kilogram object accelerate at 1 meter per second squared. That's what we found in that activity. So in other words, we can replace a newton with a kilogram meter per second squared. Remember, a newton is a derived unit. It's just a name because they didn't want to have to walk around saying, hey, look, I weigh this many kilogram meters per second squareds. Or I'm applying this many kilogram meter per second squareds of force. Right? So they named that a newton. But look what that does to our units. We've got a meter on top and a meter on bottom, and those would cancel. We've got a per second squared on top and a per second squared on bottom, so those would cancel. So we're left on top with just a 1, and on bottom with just a kilogram. So our reduced units are 1 over kilograms. Now, you can't use 1 over kilograms to understand what the slope means, but perhaps we could use 1 over kilograms to decide why the slope is what it is. This is something we'll look at in a little bit. Right? If we put 1 over kilograms here for our units, our reduced units, this might be something you want to write into your lab sheet. Kilograms are units of what quantity? Mass. So this looks like it's 1 over mass, maybe? Inverse of the mass, if you will. Right? Perhaps something about the inverse of the mass is related to this slope. So we'll check that out later after we've done part 2 of the lab here, but let's remember that, okay? And we'll use these reduced units here to help us. Now, back in the day when I used to have you write up these lab reports, I used to always want you to do a little percent error calculation to see how far off you were, right, from the class average or from the accepted value. If you want to do that, you take the theoretical value, which is 1.3, minus your experimental value, that's what you got, right, divided by the theoretical times 100 to turn it into a percent. You can see how far off you were. Right? As a class, we were pretty much dead on to 2 sig figs to 1.3. Even if we go out to 3 sig figs, we had a 1.29, right? So basically very little error. But individually, you might have had several percent, couple of percent of error in there. So why? Right? What are the sources of error? Well, in this lab, they really come from a couple of places. One is that I actually calculated that I wanted a 1.3 based on what I know of physics. And one of the things I needed was the system mass in this half of the lab. Okay? And my system mass and your system mass might be actually a little different because those carts are not all exactly the same mass. And the little aluminum masses that were on the carts might vary by a gram or two. So we might have a slight difference in system mass, which might affect our slope. Probably, though, most of the error was something that I did when setting up the equipment. And that probably is where most of the error comes from. And that is, if you remember, I tried to slightly tilt the track in order to balance out friction, right, so that we could ignore frictional effects and any angle of the track. And so probably most of your error is just how well I did this. Okay, I mean, I did not go high tech with this and make sure it was perfect. Just kind of eyeballed it, all right, and got it close. And obviously, it was pretty close because nobody was very far off, right? But that's probably where most of the error came from in this. If we could somehow do something that's maybe like an air track where it's riding on a cushion of air, and then we leveled the track perfectly, then we wouldn't have to worry about these things. We'd probably get maybe a little closer, but not much, right? We were pretty darn close on to 1.3, especially to 2 sig figs as a class average. So if this is the y equals m, our x variable is what we graph on the horizontal axis, and that, of course, is the force. Our y-intercept looks to be 0, 0. And if you actually do a 5% rule, right, your y-intercept should be smaller than 5% of your largest y value, which is the acceleration. So take 5% of your largest acceleration, and your y-intercept's probably smaller than that. But logically, it also makes sense, because the 0, 0 on this graph means when the force is 0, the acceleration is 0. Which should not shock any of you, because that's just Newton's first law, right? We didn't use the term acceleration. We said when there's no net force, objects just continue in their same state of motion. But that means they don't speed up, slow down, change direction. They don't accelerate, as we now know the term. Right? So this is really, the y-intercept here is just Newton's first law. Right? Special case of the equation that we're deriving, which we're eventually going to call Newton's second. So you don't have to add a 0. So that's our math model in this half of the lab. It's not our whole lab. We got to do the second part and take the 2 math models and put them together, but we'll get to that. And in this half of the lab where we varied the force and measured the resulting acceleration, we kept the mass constant. And your constant mass was hopefully pretty much around this, because that's what I measured with one of those carts and 4 of those masses. According to the company, it's supposed to be about 0.775, about 775 grams. But I found my cart varied a little bit, and yours might have varied a little up or down. That's one of the sources of error. But I hope you should be in this ballpark, right, within just a few grams.